Okay, welcome back. We're going to now look at yet another question from the Term 1 AP Calculus AB Standard Quiz Model. This time we're going to focus on question number 7, which once again asks you to evaluate limits, but this time we're talking about limits at infinity. So each of these limits is going to involve taking x as x goes to positive or negative infinity and looking at the behavior of the function during those times. Oftentimes this will involve some asymptotic behavior and it'll involve some cool properties of infinity that may be really essential to evaluating that limit. We're going to start with a really clean place. And again, as with all these videos, I'm trying to go in super depth and be as careful as possible and comprehensive. Remember, some of these problems you can probably do in your head. This first one, for instance, is one you could probably do with a single step, probably in your head. So just keep in mind I'm trying to give you the background information as well when I do it. So the first one here we're asked to evaluate is we want to evaluate the limit as x goes to negative infinity of 7x cubed plus 4 over 3x squared times the quantity 2x plus 1. So before I do anything else, I'm just going to help myself out and help you out by distributing that denominator just enough so that way I can analyze this a little more easily. So we've got 7x cubed plus 4 in the numerator, and in our denominator we have what amounts to 6x cubed plus 3x squared. So at this point, I would hope many of you could probably evaluate this limit just right now, instantly, and say, oh, 7 over 6. And in fact, the answer is 7 over 6. But just so that way I'm as comprehensive as possible, let me give you a reminder of exactly why it is that this is 7 over 6. So you might remember that we take the leading term, the controlling term, and we go through and evaluate the limit that way. In truth, what's happening is when we use that controlling term, we're really multiplying up and down by a single thing to simplify this into an expression we can evaluate. So what I'm going to do is I'm going to multiply by 1 over x cubed in the numerator and in the denominator. And of course, because the numerator and denominator are being multiplied by the exact same thing, so that's not going to change the value of our limit. But what it's going to do is it's going to allow us to distribute this expression in and get some pieces that we'll be able to see simplifying nicely. So in particular here, as I go to look, we're going to do the limit as x goes to negative infinity. When we do 7x cubed over x cubed, we're going to just get 7. And then for the second part, we'll have plus 4 over x cubed. So there's our numerator. This is, again, just a different way of writing it. We've just kind of divided out an x cubed, if you will. In the denominator, we're going to get 6, the first one, plus 3 over x. So this limit has the exact same value as the previous one. The nice thing here, though, is we no longer have to deal with the fact that technically both the numerator and denominators go to some form of infinity. Because, of course, if you plugged in negative infinity directly, you'd get negative infinity over negative infinity. It's not very helpful. So in looking down here, then, our next move is to actually evaluate this limit. So if we plug in negative infinity, we'll have 7 plus 4 over negative infinity cubed divided by 6 plus 3 over negative infinity. Now, I know that sign's going to stand out to you a lot, and that negative infinity, that negative might be bugging you, but keep in mind, infinity cubed is infinity, and infinity is infinity. So in a sense, both of these two limits end up being 7 plus 4 over infinity. In fact, if you want to, just so we take care of that sign a little bit better, I'll write it this way. 7 minus 4 over infinity, and the denominator becomes 6 minus 3 over infinity. So anytime you take a number, a finite number, and divide it by infinity, that's going to go towards 0, particularly in the limit. You're dividing something small by something humongous, the pieces get really small, and 0 is as small as you can really get. So in this case, that's going to give us 7 minus 0 over 6 minus 0, which in fact gets us that value that you probably could have gotten from the very beginning. So this is just a reminder of why controlling term analysis works. I'm going to try to use it in all the demos here, keeping in mind that when you evaluate this by hand on the standard quiz, you can probably move a little bit faster. So there it is, 7 over 6 is part A. For part B, this one looks really funky, and this one kind of gets people sometimes. They start to panic and think there's something weird happening here. But this is asking us to evaluate the limit as x goes to infinity of sine of the quantity pi over 2 plus 11 over x. And now if you remember, when we talked about limits at infinity in class, we talked a little bit about the fact that trig functions oftentimes are undefined. Because of their oscillation, the fact that they just keep bouncing back and forth, you might not actually have a limit. But let's keep in mind that in this particular limit, that's not what's happening here. So in fact, what I'm going to use is I'm going to use direct substitution. And you might think this is a little reckless, but again, I wrote the question, so I'm pretty confident what's going to happen. This is the same thing as the sine of pi over 2 plus 11 over infinity. So now, once again, we're back in that moment. We talked about it on the previous problem. A number divided by infinity goes towards or equals 0. So in fact, this is the same thing as the sine of pi over 2 plus 0. In other words, this is just the sine of pi over 2. And although I know that trig ratio values don't always stick with you as well as they probably should, I think you probably realize that sine of pi over 2 is actually equal to 1. So in fact, we have our nice value here in true. And again, as a reminder, what this is telling us that the graph of this function, in this case sine of pi over 2 plus 11 over x, is approaching 1 as the x values get further and further out. And although I didn't prepare for this, let me pull up Desmos really fast and just remind you of exactly what we're talking about here. So if we look at the function sine of pi over 2 plus 11 over x, there's our function. Let me look in the middle. That's kind of messy. But now what we're supposed to see is if we go further and further out, the graph should get closer and closer to 1. And notice as we look at this guy, you can probably already see that the y values seem to be pretty stable here. They just keep approaching something, and in fact if I zoom out further and further and further, we start looking at the y values, 0.9998, 0.9999, you can see that it really does seem to be asymptotically approaching y equals 1. So in fact that looks like it's working pretty well. So it looks like we found the correct limit at infinity. For part C, this is kind of the toughest one. This is definitely the toughest one. So again, I'm going to go as in-depth as possible. I know I taught you some kind of shorter ways of doing this and some ways to kind of conceptually think about it, but I'm going to do this one as formally as possible as well, just to make sure we're all on the same page. So looking here, we're once again asking you to evaluate a limit as x goes to negative infinity. This time, though, it's the ratio between 2x to the 5th plus 7x squared and the square root of 25x to the 10th plus 1. And as a good starting spot here, I'm going to begin by having us do exactly what we did on the previous one. I'm going to multiply up and down by 1 over x to the 5th. So just bear with me for the moment. So when we do that, the numerator is a lot easier to fiddle with. That's going to leave us 2 plus 7 over x cubed. So once again, since we're going to infinity, you can kind of figure out exactly what's going on. This is going to go to 0. The numerator is going towards 2. That's helpful. In our denominator, though, keep in mind that if we're multiplying by 1 over x to the 5th, that's the same thing as multiplying this thing is the same thing as multiplying by 1 over the square root of x to the 10th. Would you agree? Wait, you can't answer me. So we're just going to stick with that. So if you multiply by 1 over square root of x to the 10th, you can actually rewrite this guy as 25, 25 plus 1 over x to the 10th. Now in looking at this guy, if you go to evaluate it at all, it seems very simple. It looks like, oh boy, look, we got 2/5, and then that would be your answer. Unfortunately, that would be the incorrect answer, because in doing this, we've missed a couple problems. There's a couple issues with what we've just done in here. So we have to be a little bit more careful. And in fact, this is why I'm not a huge fan of using this controlling term analysis for these particular problems. Instead, I want us to think about what's happening with these two functions, the numerator and the denominator, as x gets larger and larger, but more and more negative along the same time. So let's think about this for a second. First, I want us to consider what's happening here. So consider 2x to the 5th plus 7x squared. As x approaches negative infinity, of course this does go to infinity, but specifically, because we have a 5th power, an odd degree, this is actually going towards a negative infinity. So basically it's approaching a negative value. On the flip side, our denominator, while still approaching x equal or negative infinity, our denominator is the positive square root of 25x to an even power plus 1. This thing is actually approaching a positive infinity, because of course when you take a negative number to the 10th power, you're going to have all those negatives pair up and it will become positive. And the square root of something positive is definitely something positive. What that tells me is that the value of our limit is going to be a negative number. So the reason I bring that up, and that's so essential for us to work our way through, is that that's the only way for us to get the actual correct sign of this particular function, or this particular limit for a function. So keeping in mind that this is negative, looking up at our limit, which you'll typically see me do in class, and again at this point it's another one where I typically do it in my head, but the idea is accurate. What you'll typically see me do is I'll focus myself and I'll realize that the controlling terms here, the ones that grow the largest, have the largest degree. So I'm going to focus my attention on them. In other words, this limit is completely equivalent to the limit as x goes to negative infinity of 2x to the 5th over the square root of 25x to the 10th. Given this, We already know that the answer is going to be negative. So we're going to get a negative, a 2 on top, over the square root of 25 on the bottom, which gives us our correct answer of negative 2/5. So there is our correct value, negative 2/5. So not positive. So again, you got to be a little more careful and think about this, that negative infinity combined with the square root is actually a function that has multiple horizontal asymptotes. So it gives us a potential for two differently signed or differently valued limits. So there's one. Moving on to part D. This is actually another function that has two different horizontal asymptotes, meaning that if we were taking the limit as x goes to infinity or going towards negative infinity, we'd actually get different values. In this case, we're taking the limit as x goes to infinity. So for this one, again, just to kind of emphasize the formalism, since the last one we kind of went away from it, we're going to positive infinity here. So I'm going to go ahead and attack this particular function the same way we did earlier. I'm going to multiply by 1 over 3 to the x. In a sense, the reason being between a constant function and an exponential function, which grows really big, I can't tell which way I'm supposed to go here, we're going to have the bigger one be 1 over 3 to the x, so we're going to need to tamp down that growth in order to attack. So from here, we'll take the limit as x goes to infinity of 1 plus 15 over 3 to the x, and in our denominator, we'll have 1 plus 5 over 3 to the x. Now, once again, we haven't talked about this one yet, but if you take a number to the infinity power, a positive larger than 1 number, of course I should add, you end up with infinity. So this is the same thing as 1 plus 15 over infinity divided by 1 plus 5 over infinity, which gives us 1 over 1 equals 1. So there's our stuff. Now this question only asked us about the limit as x goes to infinity, but for the sake of illustration, I do want to bring up for your attention what would happen if we did the limit as x goes to negative infinity. Because this function, as I said, does have two different horizontal asymptotes, meaning that we could get two different limits here. And I think you should be prepared for this situation just in case it comes up. So in this case, if we take the limit as x goes to negative infinity, you can kind of begin this problem just by using direct substitution. And in fact, that would be my strategy. I probably should have been doing that all along and seeing like, oh, this goes to infinity and infinity, but I just kind of stayed away from it. So from here, if I use direct substitution, I'm going to get 3 to the negative infinity plus 15 divided by 3 to the negative infinity plus 5. So fair starting spot, like good information to start with. Now I'll remind you that 3 to the negative infinity is the same thing as 1 over 3 to the infinity. And 3 to the negative infinity remains just as 1 over 3 to the infinity as the first time. So there's our stuff. But now once again, if 3 to the infinity is equal to infinity, then 1 over 3 to the infinity is of course equal to 1 over infinity, which means this limit is equal to 0 plus 15 over 0 plus 5. Meaning that had our limit been taken as x goes to negative infinity, we would have actually gotten 3 instead. So just because it's a limit at infinity doesn't mean you can instantly just look for the biggest term. In this case, because it was going to negative infinity and exponential functions have that flat side going on, we actually end up with a different behavior where the constant is actually growing the fastest out of those two functions. Just kind of interesting at the very least. So again, that wasn't part of the standard quiz model. Just think it's valuable for you to see. The final piece for us to attack, our plus question. So taking a look and seeing what this plus question might demand. In this case, we've got a pretty complicated looking limit as x goes to negative infinity. In this case, it's e to the x minus 5 over k minus 3 e to the x. That's one of those k questions. It says that limit is equal to 2/7, and it wants us to find k. And of course, it's not sufficient just to go, here it is, because that's not funny anymore. It's probably funny the first time when you were in like 6th grade. So in looking at this limit, once again, I'm going to play the same strategy that I did on the previous question. I just went through and I went ahead and plugged in negative infinity. So I'm going to try that same thing here. So if I plug in negative infinity, I get e to the negative infinity minus 5 over k minus 3 e to the negative infinity. Now you might be better prepared for this having done that last problem. This simplifies to 1 over e to the infinity minus 5 divided by k minus 3 over e to the infinity. And with that in mind, we said before that e to the infinity is infinity. So 1 divided by infinity and 3 divided by infinity are both 0. That means that our limit in terms of k is equal to negative 5 over k. And that means our equation or our question devolves into trying to solve the equation negative 5 over k equals 2 over 7. So from here, what I'm going to do is I'm going to cross multiply. You could also find a common denominator. I'm just going to cross multiply these guys. So when I do, I get negative 35. Actually, I'll do it this way. Negative 5 times 7 equals 2k. So negative 35 equals 2k, or k equals negative 35 over 2. It's a terrible box. So there is our final question, our plus one. Again, nothing particularly difficult, particularly in light of me doing that extra problem on the last one on part D. But there it is. You've now seen all sorts of different versions and types of questions and functions that might show up in answering question number 7 on the standard quiz.